Section 7.4 has us working with what are referred to as special products. And we're going to see how we're going to actually go through and factor these. Now what's really nice about this section is you can think of it as, and put some air quotes around it when you say it, shortcuts for factoring. Now the upshot of shortcuts is, in this case, it's going to save us a bunch of time. We don't have to go through the AC method or all of the previous methods that we have learned to get to our final fully factored answer. But the drawback with that, or the requirements with that, are that we have some very, very, very strict instances in which we can't actually use these shortcuts. And if those conditions aren't met, then we can't actually use these in any way, shape, and form. So a couple things I want to draw attention to, and if you're looking to write anything down or taking some notes out of all of this here, main ones I would recommend highlighting are at the very top here, this first bullet point. Regardless of any kind of factoring you are doing, whether it be the special products, whether it be the AC method that we've learned previously, factoring by grouping that we learned previously, anything at all, always start with seeing, is there a greatest common factor between all terms in the original expression? And if there is, factor that out. Sometimes there is, sometimes there isn't. It's always a good starting place to begin factoring from. Now the main special products that we are going to look at are three that are listed here. We have two different types of perfect square trinomials. Actually, we'll do that in a different color here just to keep consistent with what we've done in the past. And then we have what's referred to as the difference of squares. So these are the three that I recommend having written down for yourself. Make notes on them and have them memorized. Me personally, I think the difference of squares is by far the most important one to have of these three written down and memorized for yourself. The reason I say I think it's the most important one is because I think it's the most distinct and it stands out the most compared to these three. We don't very often see a two-termed polynomial show up in a lot of problems, and when it does, that could be a little bit of a red flag or some kind of a flag or a light or something going off to say, hold on, maybe something's happening here, and I could identify this being a difference of squares. If we look at the perfect square trinomials, well, our last few sections we've worked with trinomials and polynomials in three terms, so I don't think it as obviously jumps out off the screen for us to say, hey, I can take a look at some random trinomial and automatically know, hey, that's a perfect square trinomial. Maybe that's just me, but I don't think it's supremely obvious to notice and find those. But these are the three that we are looking at, we are looking for, and referencing in this section. So we'll go through a couple examples of these. How do we identify them? Some kind of, I don't know if I would say it's a process, but some things we can look for and criteria that we are looking for to determine if what we have been given in a problem is indeed a special product or not. Again, I recommend, if you are looking to prioritize anything, the difference of squares. This one shows up quite a bit, and I think it has just kind of that unique look to it at the very beginning here. So I'd say have that one memorized or prioritize memorizing that one over the other two if possible. The other two are certainly useful, but again, I don't think it's as easy to catch them. So we'll jump over and we'll take a look at a few examples of these and see how we go through and work with them. Taking a look at our first example, we have 25v squared plus 20v plus 4. We're told to factor this thing using any and all methods at our disposal. So we always want to take a look at and see, if I'm looking at this whole thing, is there a greatest common factor between all three of these terms? It's always a great starting place to get going with these problems. Now I'm looking at this and I'm not seeing there is a greatest common factor between all three of these terms. You could say that there's something between the first two terms. You could say there's something between the last two terms. And I would agree with that, but there's nothing amongst all the terms in this problem as we've been given. So that's fine. You always look for it. We always look to see, is it there? And if I can do something with it, great, I will. In this case, I can't, so I'm just going to leave it as it is. Now I'm looking at this thing and I'm saying, all right, well, this has 3 terms in it. Maybe, just maybe, this thing is a special product. Maybe I could factor that thing. My recommendation, if you were trying to determine if this is a special product or not, is to look at the first and the last term in that polynomial. So we take a look at the first term that we have here and the last term that we have here. And we notice that the first and the last term are both perfect squares. 25 is a perfect square, v squared is a perfect square, and 4 is a perfect square. So that right there is the giveaway that I might have one of my 3 special forms, or 3 special products that we had listed previously. Now I have all of those listed off here off to the side because, again, I don't think it's supremely obvious which one it is just by glancing at a problem, so we're just going to list all of them out and see which one this may or may not be. So we look at it and say, first and foremost, this thing has 3 terms. So right off the bat, we can eliminate the difference of squares from being a possibility. So we have the top 2 as our options. Well, looking at this thing, okay, the only difference between our 2 forms we have here are the signs of the middle terms. One is adding, one is subtracting. So if we look at ours, we're looking at here, okay, this thing could be that first type of special product that we have. All right, so it's got perfect squares at the very end, or on each of the, for a first term, it's got perfect squares for the last term. Great. This thing could be that first special product. Big warning to you, do not rush to assume that just because the first term is a perfect square and the last term is a perfect square, that this whole thing is a special product. Very commonly, we could see something written with perfect squares at each of the ends, but the middle term here doesn't actually align with what we need to make it be a special product. It's a very common occurrence, and just be cautious with jumping to that conclusion. A lot of people miss points because of that. So we can do a little bit of a check for ourselves to go through and see if this is the case. So let's take a look at the first term we have with this. So 25v squared. So this is a perfect square. If I were to rewrite this thing, or if I were to think on this and say, well, if this whole thing is a perfect square, what is the thing that is being squared to get to this result? That'd be the same as saying 5v raised to the second power. So 5v times 5v, that's going to give me 25v squared. Okay, so that's the same as what I have up top. But what about 4? Well, 4 is the same as saying 2 squared. Okay, so great. Now we have just theoretically found what our a value is and potentially what our b value is. Now we need to check to see if this middle term here is the exact same as saying a positive 2 times my a value times my b value. So let's check that. So if I were to do 2ab, it's the same as saying 2 times 5v times 2. So if we're to multiply all of this out, whenever we have multiple things multiplying together, we do them 2 at a time. So the first 2 things, I would get 10v times 2. Multiply these 2 things together, and I get 20v. I look at this and see, well, wait a minute, this 20v is the same as this 20v up here. Those are the same. So therefore, I can confirm that this thing is indeed a perfect square trinomial. And I can rewrite this into my final fully factored form of 5v plus 2 raised to the second power. The reference back to our notes is necessary for how to write that out. And there we have our final answer. So the big thing that we did was identify that our first term and our last term are both perfect squares. We determined, all right, well, what would the square root of each of those be? That's where we got the 5v and the 2. And then we need to check to see if I were to multiply those together by 2, that we have right here, and I get the same results, here, as in the original problem, then I have a perfect square trinomial, and I can jump right to my fully factored final answer form. Let's take a look at our second example. Here we have 100y squared minus 20y plus 1. And again, we're looking to see, is this a special product that I can factor out? Now again, my recommendation is look to the first term and look to the last term and determine, are these perfect squares? Well, 100 is a perfect square, y squared is a perfect square, and 1 is also a perfect square. 1 times 1 is 1. So this thing is a perfect square. Or the first and the last term, I should say, are perfect squares. So that tells me this thing could be a special product, which puts all three of these in play for us. Now again, like we did with example 1, let's use the process of elimination just to kind of narrow down which potential thing we're looking at. This polynomial has 3 terms, so right off the bat we know it's not the difference of squares, so we're good there. And then I'm looking at the middle term and noticing that it has a subtraction sign showing up in that, so it can't be this first form that we have, it has to be the second one. Now, like we did with example 1, we're going to identify, all right, looking at the first term, this is a perfect square, so what would this thing theoretically be as a non-square? Or essentially, what's the square root of that first term? So square root of 100 is going to be 10. The square root of y squared is going to be y. So this first term would be the same as saying 10y to the second power. Looking at the last term, 1. Well, 1's a perfect square, so 1 times 1 gives us 1, so we got to have that there. And now I need to check that if I were to plug those two things for a and b into -2 times ab, will I get this middle term here? So I'm going to write out for myself minus 2ab, and then I'm plugging in what I have been given, or what I determined for the a value, which is 10y, plugging in what I determined for the y value, which is 1, and then multiply everything together. So -2 times 10y, that's going to give me -20y. And then -20y times 1, anything times 1 is just itself. So I have -20y showing up down here. We notice that that's the exact same thing we have written up top here. Great! That tells me that this is a perfect square trinomial. Just confirmed that. And now I can write my final answer as a, which is 10y, minus b, which is 1. And then all of that raised to the second power. And now I have my fully factored answer there. And I'm good to go. Let's take a look at our third example that we have here. We have 9x squared minus 16. Similar to what we did before, we're going to look and see, is this a special product that I could factor? I'm looking at the very first term and determining, is this thing a perfect square? And yes, it is. 9's a perfect square, and x squared is a perfect square. Okay, so perfect square there. I look at my last term, I'm seeing that 16 is a perfect square, so great. My first and my last term are both perfect squares. That means our special products are on the table and available for us to use. So have those written out here off to the side, and like we did before, we're going to use the process of elimination to see which one of these could be showing up. Now, this is the part that I find, again, very, very great about the difference of squares and what makes it so useful and why I recommend having it memorized. I only have 2 terms here. So right off the bat, that just tells me these top 2 options, I'm not going to use them. It's not possible. What's even better about this is, as long as I can identify that the first term is a perfect square, and if I can identify that the second term is a perfect square, and this is the key part, are these 2 squares subtracting from one another, meaning we have a subtraction sign in between them, I've pretty much done all the necessary work that I need to identify, is this a special product? Yes, this is. So I know I can factor this thing. All we need to do now is determine, well, what's the a and the b value? And what we do for the a and the b value is say, like we've done with the first two examples, we say, looking at the first term, what squared would give me 9x? Well, we can also think of this as, what's the square root of 9? Well, it's going to be 3. What's the square root of x squared? It's just going to be x. So 9x squared is the same as saying 3x, all raised to the second power. That's 14. We look at it in a similar fashion and say, well, what squared is 16? Or you could think of it as, what's the square root of 16? In this case, we're going to have 4. So 16 is the same as saying 4 squared. 9x squared is the same as saying 3x, all raised to the second power. Great, I now have my a value, I have my b value, and I can just default to and go right to my final answer form, which is a plus b times a minus b. The order in which you write these things in really doesn't matter. The positive one could be second, the negative one could be first. Works either way. But now we have everything in our fully factored form there, and we're good to go. So again, I hope this really emphasizes, at least with the comparison of these first 3 examples that we have here, how much more straightforward and quicker it is to make sure we have the difference of squares memorized. It saves us a whole bunch of work. There's some similar calculations that we're doing here compared to our first 2 examples, but really not a whole lot beyond that. We identify A, plug it in accordingly. We identify B, plug it in accordingly, and that's about it. So yeah, there's our first example using the difference of squares. All right. Looking at our fourth and final example here, throwing one that's a little bit of a curveball at you. We're working with m to the 4th power minus n to the 4th power. And we look at this and we might think back to our previous examples and go, okay, well, I can do process of elimination to determine, well, okay, I'm not using that, not using that. This thing at most could be the difference of squares. But when we look at this thing, well, this is to the 4th power, and the form that I've been given only has difference of 2 squares, something raised to the 2nd power. So this is where we start to get into a little bit of a throwback to our exponent properties. This thing is actually the difference of squares, but it's written in a slightly different form. When we think of this, again, if we do some rewrites, this is where rewriting in this class and with math in general is very, very helpful. M to the 4th power. Well, that's the same as rewriting this and saying m squared raised to the 2nd power. Similarly with n to the 4th power, that's the same as saying n squared raised to the 2nd power. Make that first squared a little bit better here. Yeah, we'll just rewrite the whole thing. There we go. Again, if we remember back to our properties with exponents, if you have an exponent raised to a power, then those 2 things multiply together. Similarly, and same thing over here. So this is the difference of 2 squares. It's just written in a significantly less conventional and less obvious form. But it still is the difference of 2 squares. It's m squared squared. It's n squared squared. And this is where a lot of these tend to be a little bit trickier in identifying them. But again, it's worth the pause, taking some time to think on this, maybe do some rewriting like we just did right here to fully identify and see, hey, yeah, I can actually rewrite this thing, and turns out I do have the difference of squares. Perfect. Well, let's rewrite this thing then. So this is going to be written then as m squared plus n squared, and then m squared, make that a better 2, minus n squared. Now looking at the directions for this thing, and the directions with this are the same thing as written on the notes. I'm just reading these verbatim. Fully factor the following. A lot of F showing up in there with the alliteration, right? We're told to fully factor this thing. Now one of the traps a lot of people fall into, and this shows up quite a bit with the difference of squares, is we do this once, and we say, hey, great, I did it once, I'm done, I'm good to go. I can't factor this thing any further. But I would argue we can do something a little bit more with this. We have another difference of squares showing up after I factored this thing once. And thankfully, this time around, the squared that I have here, it's just a standard perfect square there. There's no fourths or sixths or eighths or anything like that. But that does mean that I can factor this second polynomial, the second set of parentheses, I can factor that further. And because I could factor it further, I need to factor it further. The directions state that we need to fully factor this thing, so we need to actually do that. So this first set of parentheses, it is not the difference of squares. We notice that this thing has a plus sign in it. Our special product form has a subtraction sign in it, meaning that this first set of parentheses is not going to change. It cannot be factored in any way, shape, and form. There is no special product, no special property, no secret method that exists to factor this thing further. Nope, it's done. It's just staying exactly as it is. The second parentheses, though, that is the difference of squares. And using like what we did before, well, the first thing was the square root of m squared. That's just going to be m. So I can jump right to my factored answer. N squared, square root of that's just n. So I can fully factor this thing, the second part, into m plus n and m minus n. And I look again and I see, is there any other special product showing up in these last two terms here? Or these last two factors, I should say, because that's what got us originally. Just turned out there was a bit more that we could do. Looking at this, I'm seeing, yeah, there's nothing else I can do over here. I can't factor it any further. I can't factor anything over here any further. Great. So put a box around it, and we are good to go. Challenge problem done. So bringing us back to our notes from the examples that we just went through, do want to again just highlight that the special products that we had right here, these are the main things that we want to focus in on having written down for ourselves and memorized for ourselves. And I personally recommend getting the difference of squares memorized because I think that's probably the most obvious one to see of these three, but it's ultimately your choice on what you would like to do with writing those down. I would like to give an absolutely massive monumental warning to you. There's absolutely no special product that exists automatically for factoring something written in the form a squared plus b squared. It does not exist. So if you're writing anything down for yourself, I would make a note of this, highlight it, circle it, star it, put red text around it, something to make it clear to yourself. There is absolutely no special product that exists for anything written in the form a squared plus b squared. There's no special trick. There's no gotcha moment that could be showing up on a test or something for it. It simply doesn't exist. Or there's no shortcut that automatically exists with that. Now, a couple other things that I do want to note as we're going through and taking a look at these final notes here with this. All of these special products that we have listed here, they can be factored using the AC method. Meaning, if you're in the boat that I'm in, which is I normally don't recognize if I have a perfect square trinomial more often than not. Which means for me, I generally default to using the AC method, and only after going through all of that do I realize, hey, I actually had a perfect square trinomial here. Okay, I guess I missed something. It will get you to the exact same final answer. It just takes a couple extra steps and lines of work to do that. All these are meant to be is shortcuts. So you are welcome to use them if you would like to. You do not have to use them if you do not want to. The AC method works perfectly fine for all of these different types of polynomials that have been given to us. As we went through our examples, I think, again, just for the sake of highlighting it, it's good to look for if the first and the last terms are both perfect squares. Big requirement in that they both are perfect squares. If only one is, we can't use these special products and shortcuts. Can't jump to the answer there. And again, as mentioned in these notes here, when you are going through and trying to identify, is this thing a perfect square or not? Well, the first term's a perfect square, the last term's a perfect square. That means this whole thing is automatically one of my special forms. Absolutely not. Do not rush the process of going through and double checking. Does what I've been given align with one of my original terms, original, I should say more original formulas that we have written down for ourselves? And then last but not least, like we saw with that last example, example 4, we can have repeated factoring showing up in these expressions. You always want to be on the guard for factoring problems that say, maybe I have to go through the factoring process 2 times, maybe 3 times, maybe 4 times. It's not uncommon for that to show up. I wouldn't expect it to be more than 2, maybe 3 instances of factoring, but depends on what you've been given. You could be asked to do more. Last thing I want to note is if you are going through and looking at the textbook does list that there is a process and some shortcuts to go through and find and factor the sums of differences and the sums of cubes and differences of cubes. That's what we have there. Some examples and the processes for those are written out on the pages there, and you are welcome to view those, write them down, memorize them as you see fit. However, for the purposes of this particular class, you will not be required to factor using these specific methods. Again, if you would like to write them down, you can, but I will not be requiring you to know them. I will not be requiring you to memorize them. I will not be testing you on them in any way, shape, and form. They're kind of useful to have just for the sake of, hey, I know that I could do that with a trinomial or something that has, maybe not a trinomial, but something that has cubes showing up. But for the purposes of this class, it's not a requirement. Now, the example problems that we went through are the ones that are listed right down here, so you can see these for yourself, write them out as necessary. And then if you'd like some additional practice problems, I'm scrolling down here just for showing these out here. So I'll leave these up here for a couple seconds, and then I'll scroll down to the final answer for each of these. But these are some additional practice problems you could try on your own. I recommend, again, giving it a shot, because if you can master viewing these things and identifying these things, these are going to save you an immense amount of time compared to always defaulting to the AC method. But otherwise, this is everything we have for 7.4. So I'll give you a couple seconds here if you want to, I would say, pause the video here. Try working through a couple of these. And then we'll go down to the answer keys here, or the answer key here shortly. And here we are, the answer key for those group problems, the extra practice problems you could be working on. Remember, always start with looking at group 1 here. First problem, is there a greatest common factor that I can factor out from every single term in the original polynomial? If there is, start with doing that, because that could make the rest of the problem way easier or way harder if you do or don't do that accordingly.